Hello, today's video will be a review of an analog multimeter, the YX-961TR. It's quite a recent analog multimeter type, one that is still being probably manufactured in China. It's a Chinese model. I'm pretty sure it resembles in some ways Western models, but also probably has some slight improvements since Western models have not been manufactured for a long time. So, why do you see two models in this picture? First of all, because these two models are somewhat similar and both may be available on the market. However, I was interested in how much of an improvement the 961 is compared with the 360. You could say that sometimes specifications show you enough about what could be different between two models. However, there are certain aspects that are never going to be covered, like build quality, or ultimately what kind of manufacturing quality or testing they have done previously to sending the product to be available on the market. And these details cannot be seen right away. You have to use the device and see how well it handles certain tasks. And this was my ultimate interest. I know very well that the 360 model is not a top of the line. I think in many ways it is flawed, and as you can readily see, it doesn't have too high or precision on measurements when placed in a different position. And this is no surprise. It's actually a model that is fairly cheap and ultimately not much to be joyous about. On the other hand, it's a decent one when you want to have the feel of using analog multimeters or for any other purpose when you want to be exposed to this technology, or you have because of various interests. So this is one of the main reasons I was interested how much of an improvement you see over here. The second one is, if you look closely, and probably you're going to notice, it has an increased range, meaning that it can use different voltages, currents, and resistance measurement ranges than the one typically above, including current, which was also I was interested to see. So these are the two models. I'm expecting some differences, but I'm not expecting anything earth-shattering. So let's see first of all. In terms of build quality, this model is flawed in some ways, meaning that right away, as far as I could tell, the scale has a problem in terms of accuracy. I'm not entirely sure that it is due to the measurement unit itself. I think it's more due to the scale that is not being drawn correctly. I cannot verify that right away, but I think there is an issue because in some ways it's strange how the device can have a reasonably accurate measurement near the beginning of the scale, and then it gets to have a slightly higher deviation when it's at the other end. And I don't know if it's an optical illusion or not, but to me there seems to be a slight deviation in how close or how far the indentations look over here, where actually the painted divisions. I'm not entirely sure if this is only due to the way I'm seeing or it's readily something that is not right. Unfortunately, I cannot measure without taking apart the unit, and this would probably result in the risk of breaking it down. So unfortunately, I cannot say much more about that. A workaround I found for this unit was to have it slightly below the zero position when in normal horizontal orientation, so that it can have an acceptable accuracy near the midpoint and then up to the end of the scale. I repeat, I'm not entirely sure if the scale is wrong or the way in which the analog multimeter is actually built, the units itself. I'm not entirely sure, but something is wrong, and I'm pretty sure it's not about the resistors themselves, because as I said before, the deviation seems to be fairly inaccurate even near the mid-range, which is actually a good indication that something is wrong. And I found this to be an annoyance, not one that is very high, but ultimately not something that I would appreciate. All right, so the next aspect is that the plastic casing is good on this model. I don't have many complaints. The rotary switch feels reasonably fine, although I have seen some that are much better. The probes themselves are nothing great, and I assume them to be quite easily broken because they have no cable strain relief. So this means that they will probably get quite quickly detached from the connection inside is going to be quite soon detached, which means that you have to be very careful when measuring, and probably you would have to repair them if you want to use them any further. So these kind of test probes, I think they are very poor, so nothing to write home about. And the rest of the device, as mentioned, is not that great. I think one of the major failures it has is that there isn't even a fuse inside the unit. Despite what it says on the top in here, there is no fuse inside. So this device was quite poor in many ways. However, it's usable, and if you want an analog multimeter just to have fun with, I think it's all right. The newer unit, I was expecting it to be slightly better, and we will see if this is the case. However, I noticed right away the fact that the zero position is wrong. And you may wonder how much this will affect you in practice. Well, quite a lot. It's a disappointment that it doesn't even come at least reasonably calibrated out of the factory. So this means that you would have to fiddle with the unit, and this of course raises doubts about the specifications you may find, but ultimately we will see what happens. So I'm going to take a AAA battery that should have around 1.5 volts. I'm going to verify the scale to be at around the range to be at 2.5 volts, and I will plug it. So I think this will show us how good or bad the unit is right out of the box. I'm expecting 1.5 volts all the way about. I'm going to place it in the correct polarity because, as you know, with analog multimeters you cannot use the reverse polarity unless you have one that has a zero position in the center of the scale. And let's see what... All right, right away I can see a difference when measuring with this multimeter. It's a bit above 1.5 volts, which is actually quite close to what I'm expecting. And let's see, we have 0.5 to 0.5 volts. I'm going to place it right here, and let's see what kind of indication it offers. So 2.5, 1.5 volts should be, oh sorry, I made the wrong polarity. One common solution to avoid stressing the device too much is to make a sudden contact, and if the scale goes in the scale, the measurement device shows it going slightly in the opposite direction, then you can turn it immediately and there is no damage. So this is one of the aspects. Just press slightly, and if you went wrong, because you can see that it's easy to go wrong, you can recover immediately. All right, so now it's the right polarity. Let's see. It's a bit above 1.5 volts. I think this is actually quite spot on, because As you can see, it's right there. So 1.5, 1.51 or 1.52. Actually, this is a good enough value, but as I said, I modified the zero position. So I'm not entirely sure if this should have been the case, but it's actually a good readout. Let's see how much this multimeter shows. I'm going to use the same orientation, and it goes a bit above 1.5. You can readily see an interesting difference between those two. The fact that this one slowly deviates on the scale while the other deviates quite faster. The faster response may be a good behavior in certain situations, but most of the time it's not that good, because it would mean that the internal spring mechanism is actually stronger, and this means that in some ways the measuring accuracy may not be that good. Newer and more advanced multimeters have a slower deviation rate, so when they are actually going through the arc, they move slower, and this is in general an indication of a better quality multimeter, or at least in terms of how it creates the readout. In terms of the construction, you can readily see that this strip that is having mirror appearance to it is not of a very high quality. It's just the part that was painted in white, it's being left uncovered. So I'm not expecting it to have a very good performance, and you can see right away if I'm moving towards a vertical position that there are angles at which it's not clear what the readout is, and I think that this is a small concern, but again, with multimeters in this kind of price range, I'm not expecting higher quality. The case itself feels somewhat cheaper than the one I had before, so this is clearly something to be said. I'm noticing some issues in the molding, and this is one of the telltale signs that the molding was not particularly of high quality. And the device itself, when purchased, was like that. So actually it goes on to show that the precision molding is not great. All right, what about the probes? I think that the probes are an improvement compared with the ones of the other multimeter. They have a much tighter connection, and this means that you have improved accuracy and a better mechanical performance. However, the ends are still, as far as I can tell, having no strain relief. In some ways they feel even lighter than the ones on the other multimeter. I'm not entirely sure if this is due to the cable, because I can see that there is a difference in cable width, or if this is due to the fact that the internal conductor may not be copper but actually aluminum. This is actually something that happens in the case of products manufactured in China for cost-saving reasons. So I'm not entirely sure if I'm having here a true copper conduit. The 0 ohm position is made through this, is adjusted through this potentiometer. I see again some signs that the molding of the knob was not particularly great, and I'm seeing a slight off-centering issue. However, my biggest gripe is that the rotary switch feels outright horrible, in the sense that it doesn't have a definite balancing on any particular position. So this quite clearly says that they have cheapened out on that. And unfortunately, it's one of the aspects that you will use for a lot of time, but you have to understand the limitations. So this one is clearly a place where they made a lot of savings, and probably not in the best way. I could have accepted the savings in other areas, for instance, not having transistor testing capability, because I think this one is mostly obsolete, and with a device that doesn't have too much precision, I think this feature is not required. So this would have been a better place to make an economy rather than the rotary switch, which along with the dial itself are the most important parts. Alright, so this is the initial evaluation. Let's see right now what happens if I'm going to try and make the zero position better. So I have to have a screwdriver and then turn probably in that direction. It was stuck in that position. Okay, as far as I can tell, I think this one is as good as it gets. Let's see if this one affects our initial measurement and makes it slightly more accurate. I'm expecting it to have a slight impact. Oh. Well, that was unexpected. And I think what went wrong is that part of this adjustment could have made the device indicator get stuck in a particular position. All right, so let's see if I can put it in a somewhat similar position, and if this one is going to help, or I damaged the multimeter. Oh, it's very interesting. So there is no damage, but this goes on to show that it's a failed design. Just moving slightly, rotating slightly, this adjustment shouldn't have made any higher impact than just forcing the dial to have the perfect zero position. It shouldn't have influenced how much it deviates on the scale. So I think this one clearly goes on to show that there is something wrong about how they designed it. Let's see how much of an influence does it have. Okay. Yes, this is a major design flaw. Let's see what happens if I'm going to... Okay, so I can safely assume that I cannot go... Oh, no, it seems to be working, but I'm not entirely sure if it got... Yes, it got stuck. Okay, so this is clearly a design flaw. Let's see. Yes, it's horrible in this respect. I have never seen an analog multimeter making such a behavior possible. So yes, this means there's probably no meaningful zero adjustment is possible. Yes, that is very bad. Let's see if I can make... Okay, so that is... if I'm going to go slightly lower... Okay, and let's test just for the sake of it if the full deviation is possible. Okay, it's possible. This means that probably there is a misalignment or a problem with the angle at which some parts are being placed, meaning that they can influence the rotation of the dial. Oh yes, horrible. Okay, let's move on. So no meaningful zero adjustment is possible. It's somewhat similar with the issue we have on the older model, with the exception that in that case it didn't affect the deviation. It just affected the possibility of proper measurements. All right. Now we are going to test a 9-volt battery. As you can see over here, 2.7 amps at 9.2 volts. It's actually a very powerful 9-volt battery, and it's interesting in many respects. So let's check the high current measurement capability. Sorry. Okay, just because the device is very small, it means that it can tip over easily, and working with one hand, it's not really recommended. Okay, so I placed it on the 10 amps range, and I'm going to move towards the scale, the proper range on the rotary switch. So let's see right now if it shows this amount of current. Right, the 9-volt battery is placed, the correct polarity, and let's see. So 10 amps, 2 amps, yes, around 2 a bit above 2.5, probably 2.8 amps, if I see correctly. Yes, between 2.5 and 2.7 amps. I think that the value is quite reasonably accurate. In general, high current measurements are not particularly good, because you have to understand the fact that when you are measuring in short circuit, you're actually limiting yourself, first of all due to the multimeter, and then due to the battery's behavior. So we have to understand that this value is only something that you use as a relative reference. All right. Next, we should try some other batteries and see how much or how well they measure. I think that the next important detail is with a small coin cell battery, the standard CR 2032, because as you can notice on the writing, it had 7 milliamps current capability, and now it drops to 2.6. So we can readily see how much current it still delivers. I have measured this amount of current with a digital multimeter that is reasonably accurate. I actually compared the value with two digital multimeters, and they both offered roughly the same value. So I'm expecting the situation to not have any particular difference. So using the correct polarity, the plus is the larger one that also has this slip, and the negative is on the exposed connection on the other side. All right, so it gets to around 2. It's okay, 2.5, 2.6. It gets over the maximum scale, so I should go on the 25 milliamps range. And on the 25, we can see that it gets a bit above 2.5, 2.6. Yes, around 2.6, I think is a correct now. It seems to be at the 3 milliamps range. So quite an okay value. I don't think there is a problem. Again, we are not testing something in the same condition. Just about any multimeter places a different load on the battery. So this means that in some ways current measurements are never as accurate as voltage ones, and you have to take that into account. The next measurement possibility I see, and I think it will be interesting to notice how well it measures main voltage. So 250 volts, I'm expecting something around 240, and let's see if everything goes smoothly. Okay. So it's clearly over 225, and if I'm looking correctly at the, yes, it's around 240. All right, so a good value. For your precaution, never touch the probe tips, the other probe tip, when you are extracting them from the socket. Right, what about the tips themselves? I think they are well machined. They are certainly better machined than these ones, because these ones are highly inconsistent. I think one of them is relatively straight, the other is slightly bent, but you have to understand they were not put into strong distress environment. Alright, let's measure the other batteries, and I'm expecting roughly the same performance, and then we will take apart the unit. Okay, let's see. So we are on the 10 amps range, and I'm expecting a value of 5.9 amps, or probably 5 amps. I don't know how much we will find over here. Okay, it was around 4 amps. Less than 4 amps, 3.5, something along the line, yeah. 3.5, 3/8 probably. Okay. You can see that when I'm making a different connection on one of the batteries connectors, the value slightly deviates. This is normal. In general, better probes would have helped, but this is the issue. Okay. So around 4 amps I think is a good readout. And in the case of this battery, it will probably be more than 1 amp. I don't know exactly how much. Okay, it was less than 1 amp, around 0.6 milliamps, 0.6 amps, yeah. I think we saw enough of the device, so let's tear it apart and notice what happens. I could have also made some measurements about the battery capacity, but in general I do not use and trust this scale for a couple of reasons. Although it's interesting that some multimeters have this, in general the approach by which they show a battery as being good or bad is not, in my opinion, as relevant as the one about measuring the maximum current. Okay, so again, switching to the normal measurement probes, and let's see. Oh, yes, I made a mistake. This can usually happen, 1.5 volts, and let's see if they point at the battery being good or not. Oh, interesting. I wonder why. Either we are not making good contact, or there is no measurement capability. Okay, we didn't make good contact. So it shows as a battery that is somewhat good. It's very close to the green side. As I said, this measurement is not accurate. Probably if you're doing more measurements, it is a good way of assessing battery's performance, but not with a very exact reading. So if you're just making quick measurements, it could be good, but I'm not expecting it to be entirely accurate. Okay, so we can see it right at the green position. Alright, and let's see the 9-volt battery testing capability. I'm expecting this battery to fare on the green side because it's actually delivering a very good current and a very good voltage, which, by the way, we could have measured before, but it doesn't matter. We can measure again after. Okay, it's clearly on the green side and towards the end, so it's a very good battery, and this was what I was expecting. Because when we measure the current, I think it delivers around 2.7 amps, which is a lot. So let's see right now how much voltage it delivers. So we are going on the 10 volts scale, the 10 volts range, sorry. And let's see. it is 9 volts, 9.2 volts. Okay, let's see if I can have a better readout. Unfortunately, I have to turn it slightly sideways so that I can see it better. Yes, 9.2 volts, so it's spot on. Alright, so actually my only concern up until now is the fact that you cannot have a good zero position, and this doesn't translate into very high measurement accuracy in some situations. Other than that, I think that the device has reasonable accuracy. So let's see what kind of details we can glance from the operator's manual. Alright, so it presents the multimeter, series capacitor, terminal. Alright, I have noticed this also. Output is for testing capacitors. Alright, it's interesting. Range scale selector, switch knob, measurement terminal, scale reading, zero corrector, zero ohm adjustments. Okay, measuring terminal. Zero corrector is adjusted to place the pointer on 0 of the scale. Okay, it need not be repeated but the position of the pointer on 0 must be confirmed before starting measurement. What is interesting, as I mentioned, setting the 0 position should not have made it impossible to measure properly. So actually we have a design flaw, but it's clear that since it's not presented in the manual, this shouldn't have happened, and I actually never saw a multimeter do just that. Okay, test lead connector. The test lead attached are inserted. Okay, selecting a range, we don't need to look upon that. However, what is more interesting is the specifications sheet. Alright, so let's see if we can have a proper way of showing these details. Alright, so as you can see right away, we have a lot of measurement ranges, and this is good because ultimately on an analog multimeter you lose a lot of precision when you are close to the limits of a range. You don't have the ability as in digital multimeters, where values are shown reasonably even when they are close to a defined to have a rough understanding. When you are measuring, let's say on the 10 volts range, the measurement accuracy is not as much affected if you're measuring close to 1 volt or measuring 10 volts, because you have the same readout capability, the same precision. On the other hand, with an analog multimeter, you lose a lot of accuracy when reading small decimal values. So you need a lot more variation on the measurement range. Okay, the AC current plus or minus 3% deviation at full scale deflection. This is the typical value, but again, with the behavior I noticed over here, I'm not entirely sure if this is entirely let's say possible. Input resistance 20 kilo ohms per volt. In general, having a higher input impedance makes it possible to have a higher accuracy. Unfortunately, this may not scale well if the device itself has some design flaws. This one has also 20 kilo ohms per volt, so the input impedance is similar. This means that the measurement accuracy should be roughly similar. For AC voltage, we can see right away that the input impedance is lower. This is typical with most analog multimeters, and the measurement accuracy drops. You are using rectifiers, which means that probably you're not going to have the same accuracy. And moreover, you're not even using probably a bridge rectifier, you're going to use a simple or a dual rectifier, which means that the voltage you're going to measure is not going to be correctly determined. It's going to be a rough estimation, and this estimation goes towards worse results when you're going to reduce the number of components being used for rectification. In the DC milliamps range, yes, you can see right away that you have the same accuracy as on the DC voltage. The resistance 3% of arc, which means that you have a different precision based on how much the pointer deviates, which means that resistance measurements is not going to be better, and this was one of the major flaws of analog multimeters, the fact that resistance measurement was measurement accuracy was very poor, and this is due to the fact that the scale actually is logarithmic, not proportional, which means that some values can be more or less determined with a rough estimation, and this gets worse as you get close to the initial resting position of the pointer, which means that you have to rely on much more measurement ranges, and even so you may not find one that is particularly suited to your values. Alright, battery 0, 1.5 volts, 0, 9 volts, within 5% of the arc, so you can readily see that the precision is may be considered to be slightly lower, similar to the one on resistance measurements, which means that the scale is logarithmic, not proportional, and again this goes on to show some issues. And the next important fact is that there is a load placed on the battery, 250 milliamps for the 1.5 volts battery and 25 milliamps for the 9 volt one. I think that the load should have been higher, because ultimately when you're going to test some devices, you have to think about how well they handle certain loads. But this goes on to show that the way in which we assess a battery's performance is mainly due to the amount of current it can readily offer at a specific voltage. And of course, this is not a measurement that can be entirely encompassing. However, it's one that is good enough, and there are battery testers still being available on the market that have an analog multimeter inside them. So actually this goes on to show that there is a specific methodology that is being applied, and I remember roughly those same values also in other instances. I'm not entirely sure if I have seen them also on digital multimeters or only on analog ones, but I remember these values from other places. All right, AF output, this one should be audio frequency. All right, I have never used and I'm not entirely sure what kind of accuracy we can expect from that. Leakage current terminal for terminal to terminal voltage. All right, I'm not entirely sure what this would mean. Current amplification factor, yes, this is for testing transistors. And as we can see over here, we have the measurement ranges. Okay, I think it's quite clear. Some other suggestions for making measurements, nothing that cannot be assessed through directly operating the device. And what we find on the back side, and I think this is very useful to know, is the circuit diagram. And this one matters a lot because it can tell many details about the device's construction. As you can see right away, it has a position for an internal fuse. It's 0.5 amps, which means 500 milliamps. The highest value that could be read on the small DC currents range is 250 milliamps. So having fuse rated for 0.5 or 500 milliamps is a good design decision. Of course, if the fuse is present, but we assume that this is the case. All right, we can see the 2.5. This should be the higher current connector. And I'm not entirely sure why it doesn't say 10 amps or 25 amps, because 2.5 is certainly strange. 2.5 amps. Okay, but it doesn't have a position for 2.5 amps. So probably they use the same schematic for the 10 amp modified multimeter when they should have had a different schematic for the 10 amps one. Alright, let me look just a bit. Unfortunately, I cannot determine the value of this particular resistance that of course is being used as load for the circuit. Okay, I think that this one is quite a bad situation, because we cannot determine what was the value and have a straight answer if this schematic was being used for the 2.5 amps model and they just placed it on the 10 amps one as well, which is wrong, or if they actually mislabeled the connections that's having the 2.5 amps. These are actually some of the details I am highly interested in when I see such multimeters made by unknown or let's say various brands, because I'm not expecting quality consistency, and clearly we can see that this is the case. What else should we see? Yes, we have two diodes. I assume that those two diodes are for protecting the analog multimeter measurement parts, and there is another one. Okay, AC voltage, and the AC voltage seems to pass through a single diode. Yes, so it's half rectification, which means that it's not full square wave rectification, which means that of course, as is in the most situations, you will not have a higher accuracy when measuring AC voltages. This was to be expected. Alright, and I think, and you can see right away another thing that is a telltale sign of a mistake. Just a moment. This is a way to signal on the circuit diagram that there is a LED placed in that position. As you can see right away, there is no LED being placed at any position. And there is something else that seems to be missing, the fact that this device has a buzzer, and I do not see anything that would suggest a buzzer. Okay, so this device doesn't have a buzzer. Sorry, I made a mistake. This device had a buzzer. Although, I think it could be inside the device. Okay, yes, it does have a buzzer. You can see over here the indication. I mentioned it correctly the first time, but I was expecting to see some holes placed for the buzzer so that it can make more noise. Alright, let's take apart the multimeter and see what is inside. Let's see if I can make a reasonably accurate focus. Okay, we have a single screw. This is actually typical. The same was for the other multimeter as well. Okay. Oh, what we see right away. The build quality is not bad in most ways. I mean, I can see right away the fact that they included 250 volts, half an amp fuse, which is actually a major improvement compared with the other one. I can see right away, or I can recognize right away the fact that this is the high current measuring resistor, or in this case it's a copper conduit that is being used to measure the drop. I'm not seeing a particular high clearance in this area, and I think this one is less than expected. There should have been some clearance from the board so that if it gets slightly hotter, it will not affect this particular resistor. So this means that the circuit design was not as optimized. 10 amps, yes, it's correct. All right, we can see the connector for transistor measurements. The other parts seem to be of reasonable quality. As far as I can tell, these are 1% resistors, so they should have quite good stability in time, and they should have close to their initial values. We can see the branding over here, the two fuses being used, actually there are four diodes being used. So there could be a full rectifier. I'm not entirely sure if this is the case. We don't have the schematic, and I will not dwell too much, particularly because this device doesn't have good enough accuracy to mandate such an analysis. The 9 volts battery connector, the standard, I think it's, yes, it's AA. No, it's AAA. Yeah? Let's see which ones do fit. These are for the ohms, the resistance measuring range. Okay, let's see how well they stand over here and what kind of durability we can expect. Okay, right away I can see an issue with making a good position. You have to force quite a lot such batteries. I'm expecting this to be a problem because or not to be such a high problem because Chinese batteries seem to be slightly shorter than the American or European produced ones. So I'm expecting it to work even if they look quite, as you can see. Okay, let's see if I can make a better connection, but it's going to require a lot of force. Yes, it can be done. However, as far as I can tell, there is a lot of pressure being placed over here, and the poor mechanical design means that it's probably not going to withstand a lot of use. Okay, let's see how resistance measurements are. So we are going to place the device quite finicky. Let's see. Let's move the range towards resistance. Okay, so I think that on the highest, let's see if this one goes for any particular range. Okay, not working. So this could mean that we need to use the 9 volts battery to measure resistance. It could be, it could be. Let's see. It's kind of difficult to make the connection with a single hand, but we will achieve that. Okay, I think we made quite a good connection on one side, yes, and the other as well. Let's see how well we can place it. Okay, good. So we are now ready. What happened? Not a good enough connection? Yeah, not a good enough connection. All right, so I have fiddled with this potentiometer, with this adjustment, but I'm pretty sure it wasn't as high. So actually, this goes on to show that the device is not calibrated at all right out of the manufacturing line. And each device should be separately adjusted because there is some variation. Okay, so I think that these measurements are consistent. Let's see. Another range. All right, another range. All right, and the top of the line, the highest. Okay, this one is clearly off. So yes, the buzzer is strong, and I'm pretty sure it's going to have the same amount of capability even when we are placing it on the case that is fully closed. Let's see. Yes, it's a good buzzer, nothing to complain about. I was also wondering if... yes, it doesn't reach the full scale. So we still see the old problem of most devices, that they have no compensation based on the resistance range, which would mean that you would have to use the potentiometer on each and every range when you are going through them, probably in order to make sure that the value is properly measured, and on some ranges the deviation from the zero position is going to be higher. This is actually a typical scenario, but it goes on to show that there have not been major improvements in this area. As you have seen right away, you require a 9-volt battery in order to operate on the ohms range, or the resistance measurement range, which was somewhat expected, but I would have hoped that a different design would end up not requiring the device to be powered by the 9-volt battery. First of all, because 9-volt batteries are more difficult to find and they have a lower service life than 1.5 volt. Oh, okay, so you can't operate. That's interesting. If you don't have the 3-volt batteries. Oh, very interesting. Okay, so you need both of these batteries in order to operate the device. So this means that you have to provide around 12 volts in order to properly initiate the resistance value measurements. I think this is not a great situation, and let's compare it with the other multimeter I had over here. So I'm going to take it apart and let's see if the situation is similar, because I'm very curious about that. Okay, the situation seems similar, and I assume if we are going to take out this battery, okay, this is the other one. As you can see, the construction is poorer on this one, and I have found out this long time ago. Let's see if we can measure resistances with just the 9-volt battery, or we have to have the full complement. Okay, so it's the same design. Yes, as we can see, switching from one range to the other doesn't make the needle move. So you actually require both the 9-volt and the AA batteries to measure resistance. What this does tell us? Well, I'm pretty sure that measuring resistance is a failure in most respects, because you have to make so many adjustments due to the port, because the batteries are going to have a different wave that occurs on them. Oh, an important part, it seems that over here the batteries can have connections that are slowly failing over time, because they have they don't have a stronger connector being placed over here. I think this one was the original screw. All right. Okay, it went over, so I'm going to place it at another time in the proper position, and we can readily screw again this meter. Since I'm not going to measure resistances with it, because there are so many things that could go slightly off my expectations, I'm going to take out the battery and use it in other devices. This is actually one of the major advantages of analog multimeters, because except resistance you can measure just about anything. Okay, I'm having a slight issue trying to take out the meter. Okay, it was successful. Yeah, unfortunately this is the situation. So what is my overall perception on the, okay, sorry, this was my mistake. I should have placed it in a different way. I bent slightly this cable because it was hitting the bottom of the case. I think this one goes out to show again that there were some cost-saving solutions that were not particularly good, because they made the case that is so close to the actual internals of the multimeter. It means that any sort of mistake in placing the cables is going to have an effect. In this case, I think it's better to place them like that, because they will be better protected. But this goes on to show that the construction is clearly not the strongest point of these multimeters, and they all have similar failures. Okay, let's see right now. I think that it's properly placed. Yes, it is. And we can screw back the case. All right, so what is my evaluation of the multimeter? I think in many ways it still fails as being a reasonably accurate or well-built device, and you can see it in the casing, you can see it in the measurement unit itself, you can see it in the rotary switch and on so many other places. But again, if you want to have the experience of using an analog multimeter, and particularly if you want to have a specific range available, because one of the interesting parts is that it does have a current, high current measurement capability, and the low voltage measurement is clearly better than in some other devices. It's 0.1 volts compared with 0.25. It means that you have a device that is quite versatile. However, do not expect very good long-term performance. You have noticed the issues I had setting the zero position, so I'm not entirely sure what will happen with this device, I don't know, 5 years down the line if it's used frequently. The test probes, clearly they are a step up from the poorer ones they used before, but still not everything is perfect, and particularly their low weight makes me question how much conductor they used, and if they are going to properly withstand years of use. And there are other aspects that have been constantly an issue with multimeters, like requiring multiple batteries, and this has not been solved, and having relatively poor accuracy in some instances. However, I don't think that the device is bad itself. Again, at a dry price, it could be a good purchase, and particularly if you want a relatively new multimeter. It's clearly not up to the level of 1960s, 1970s good multimeters from reputable manufacturers. It can never be in accuracy, and particularly not in reliability. I mean, there are so many things that are already questionable in this product. However, if you want to have the experience of using an analog multimeter and having a better understanding of our current technological capabilities, I think that this device is good. But again, at the right price. I don't think that it should be pricier than 10 euros or around $12, and even so, it may not be on the same level at which you can find some digital multimeters. And considering the limitations of analog multimeters and their build quality, I don't think they should be at the same price point as digital ones. Ultimately, I'm entirely sure that this will not be the case in the next few years, because analog multimeters are not going to be manufactured anymore. It's clear that around 2008 was the last time analog multimeters were really being developed, because I have seen another manufacturer that has only improved his product lineup in 2008, and it was from China. It was about Olsun. So I'm entirely sure that these multimeters are slowly going to fade away. There are going to be various products still on storage that may be available for sale. but ultimately we are not going to see any sort of improvements. And there could be some improvements being made on multimeters. There are still some ways in which the circuit could be made more efficient, and cost could be saved. For instance, surface mounted components could be used. On the other side, I don't think there are many ways in which an improvement could be done, because you're still facing the same mechanical limitations that you always see. And even if the measurement unit itself would be of a higher quality, there are other aspects that are going to create issues, like still having to be careful about polarity, the risk of burning the device if you're using the wrong polarity, the fact that when you're on a particular range, you don't have a way of safely limiting the deflection of the pointer, which means that it could be affected if the value is higher than the one you were expecting, than the range you expect. So there are so many things where you have to take initial precautions, as you did with devices 20 or 40 years, which compared with the convenience of digital multimeters that can just withstand so many things that are beyond their measurement capabilities, really make the case for an analog multimeter very difficult to present. So I'm pretty sure that there will be only certain devices that will be made by hobbyists and probably passionate individuals that have the necessary means to design and release on the market such a product, because the mass market ones are not going to be available, and the ones that are available right now most of the time are of questionable quality. So ultimately this is a niche market. I'm entirely confident about that. I can find a slight use for these devices, and I hope you will find them as well. However, there are many limitations, and you have to understand that, and some of them are not due to the fact that you are having an analog multimeter, but just that you are having a cost-reduced multimeter that has so many design flaws, and they are unfortunately quite consistent in that respect. So, is this multimeter recommendation? Clearly not, but if you know what you are doing and you accept those limitations and you want to see and understand how people handled technical activities some decades ago, I think it's a very good showcase for that. But ultimately, for just about anything else, if you want accuracy, if you want speed, if you want features, a digital multimeter, even one that could be as low as 5 euros, is clearly going to be much better. 5 euros, or I don't know, $6 will be much better than this analog one in reliability, in performance, in features, in just about any respect. Is going to be better. So I hope you enjoyed the video. It was quite a lengthy one. Perhaps it was my mistake that I tried to make cross comparisons between those two models, but I hope you find it interesting, and thank you very much for watching.